This is Jim Smith. I'm the Midwest Regional Manager for American Wood Council, and as Marcy just noted, the presentation today will be Tall Wood Structures Fire Resistance Design Primer for Mass Timber. This is basically the AIA slide that provides you with information you're probably already aware of as to how you can go about checking up on and how you will be provided credit for the webinar today. This is the course description. Hopefully this is the description that you looked at when you decided you wanted to join the webinar today. So this shouldn't be anything new for you. And the learning objectives, basically what we're looking at is the hopefully to give you a feel for how mass timber elements behave in a fire, understand the basic methods that the 2015 IBC recognizes for achieving the fire resistance rating of wood assemblies, learn about the calculation methodology for wood assemblies and mass timber, and learn a little bit more about CLT and the future code change concepts related to taller and larger mass timber structures. And with that, we're on our first poll question. Marcy.
There we go. So this one's always the easiest. What's your profession? We have about 59% engineers, 21% building officials, 10% architects, and just a little smattering of other and fire officials here. No matter your profession, we are so happy that you're here, and welcome.
Well, here we are, cross-laminated timber. Mass timber as a separate building system was really born because of one new product, cross-laminated timber, or CLT. CLT represents essentially a sea change in wood construction because of the new structural and fire resistance characteristics it represents for wood construction. Never before had we contemplated solid wood floor and wall sections of this size, or this mass, used in a similar manner to that of concrete walls and floors. CLT is typically dimension lumber, 2x laminated, in crosswise fashion, layer upon layer, with glue layers provided between to make a solid wood floor, wall, or roof panel up to 20 inches thick and 60 feet long. What has been used so far is typically more like what you see here on the screen, panels between 6 and 9 inches thick. So imagine a building put together as shown on the right with solid wood floor and wall sections, a very significant increase in structural capacity for load-bearing walls and floors. It will enable taller buildings far beyond the normal capabilities of repetitive member systems of traditional or engineered joists, studs, and rafters. And it will also have very different fire resistance characteristics that come along with its mass. The reduction of wood surfaces in solid wood assemblies as opposed to repetitive member assemblies, and the way it will respond to fire. This picture, and you'll see it again at the end, but what we wanted to do, and the reason for providing this slide, is to give you a perspective that will give you even a better idea than that previous slide as to just how large and massive these CLT panels can be. This is from the erection of the two-story structure erected inside the ATF fire test lab in Maryland. Here's just gives you an idea on what a mass timber building looks like while it's under construction. This one is using CLT for the floors, the big glue lams for the vertical structure, with some CLT walls for the shafts, like exit enclosures, elevator shafts. You can see that this differs differently conventional framing and also from conventional heavy timber buildings. Just for your information, this is the Arbora building in Montreal. At the time, it claimed to be the largest residential CLT project in the world, made up of 434 condo, townhouse, and rental units in 3 8-story buildings, all made from sustainably harvested wood, turned into panels by Nordique CLT. Its design was by LeMay plus CHA. This is basically what has come to be known as mass timber, or new systems for wood construction that we haven't seen before. It's going to be different than those systems of the past. The light wood frame, the post and beam, and then on the far right, this is the way these newer structures look like when they're up up and under construction. What I provided for you here is a slide that shows the CLT wall tested in October of 2012. The wall itself was loaded with 87,000 pounds or 87 kips. It's important to note that that's the maximum load that the rams that were provided or that were available at the testing facility that they could apply. So it was loaded to the max. The vertical load held throughout the test. The test specimen in the E119 test, for which we have the picture here, had a half-lap joint right in the middle of the panel. Even though we were hoping for a 2-hour fire resistive rating when we started, the failure occurred or it lasted. The test lasted for 3 hours and 6 minutes, and the failure was due to the flame through and that endpoint criteria. You can see on the left-hand side of the picture, the flame through. The CLT panel was still carrying the 87 kip load at this point in time. Now I'll touch on the IBC principles associated with heavy timber and mass timber. Before we get too far into that, what I want to do is take a look back, or kind of a step back, and look at some of the more basic principles of the IBC. Non-combustibility and fire resistance are two different things. And they each have their place in the code. The code requires non-combustible materials for some purposes and specific fire resistance ratings for others. You can have a non-combustible building element, such as a steel column or a cold formed steel wall, with little or no fire resistance. So the non-combustibility is there, but not the fire resistance. With no protection, the steel elements will fail quickly in a content fire because basically 1,000 degrees, 1,020 degrees Fahrenheit, the steel loses 50% of its strength. And at 1,380 degrees, it loses 90% of its strength. Conversely, you can have a combustible building element, such as a heavy timber or heavier mass timber, wood beam, wood frame wall that has high fire resistance. Because of the inherent fire resistance of the timber, which retains its strength even while burning, or the fire resistance of the non-combustible covering of the wood structural elements, or both, has high fire resistance and can perform its function for a long time in fire conditions. Just so you can equate the temperatures that I referred to before, the ASTM E119 fire test, a temperature of 1,000 degrees Fahrenheit is reached at 5 minutes, 1,300 degrees Fahrenheit at 10 minutes, and 1,550 degrees Fahrenheit is reached at 30 minutes. That means that shortly after 5 minutes, the steel is at 50% strength and 10% strength after only about 12 minutes. So we said that we can summarize the fire resistance requirements for traditional heavy timber by saying that the minimum sizes are required for the members, the columns, and the beams. As currently used in the IBC, heavy timber typically refers to one of the types of construction and relies on the dimensions only to provide an undetermined level of intrinsic fire resistance, but not a specified fire resistance rated. This has commonly been claimed as being in the ballpark of 45 to 60 minutes, but can be more in a highly loaded or a lightly loaded structural condition. So now when you go into the heavy timber, this is the column that you can take a look at. This is the current requirements for conventional heavy timber. It's table 601, provides the fire resistance rating. You'll note that in general, there are no fire resistance rating for heavy timber elements. Why? Because the fire resistance is considered to be provided by the minimum required dimension of the wood members, large dimension columns, beams, decks, etc. Conventional heavy timber type 4 building elements are defined in the text of the code with the minimum dimensions of members specified. All the building allowable size requirements and the other requirements of the code in regard to fire and life safety are related to past performance of heavy timber and fire. It has good inherent fire resistance by virtue of its size. In some areas, it's credited for roughly 1 hour of fire resistance. I won't get into the details of where that is. There's some footnotes where there's trade-offs like that. Here, what I've provided for you here is the 7 methods that the code recognizes for establishing fire resistance. They're all based on the same standardized testing, the U119 testing that I referred to earlier, but an assembly does not have to be individually tested to be recognized by the code. Of the 7 recognized methods for determining a rating, what I have up there in red is that's the one we'll talk about next, IBC Section 722 on the calculation method for exposed timber elements. This is just basically a graphic to explain some of the basic understandings behind the calculated fire resistance of exposed wood. It's low thermal conductivity, dimensional stability, predictability, and the portion inboard of the char remains cool, which means it does not lose its strength. The calculated fire resistance is provided in the code is called out in IBC Section 722.1. It references Chapter 16 of the NDS. And then what we show over on the right is our technical report number 10, which provides background on the research and examples on performing the actual calculations specified from within the NDS. This is what we have here is a graphic representation of the science and concepts behind the calculation of fire resistance. The diagram at the right shows how a beam with fire exposure on 3 sides is designed. Ultimately, based on the remaining unaffected breadth and depth after the desired time of fire exposure. Just another example. This is, as mentioned in the CLT handbook, during the early full-scale fire research on CLT, small pieces of the charred layers have been observed to fall off when the temperature at the CLT lamination surface, or the interface, the glue line, approached 550 degrees Fahrenheit. That indicated an adhesive failure. Loss of the char layer when the char front reaches the glue line effectively resets the nonlinear charring rate used in the NDS methodology, resulting in a slightly accelerated charring rate. Therefore, the char depth model used in the fire resistance calculations is increased for effective char depth of CLT when compared to sawn or glued laminated beams, which did not have that, or which were not affected in that manner. And these what you see here, these are the charring results based on the CLT laminations of equal thickness. The commentary has provisions for laminations of unequal thickness, but this table is provided for basically the laminations being of equal thickness. Note that the table provides the effective char depth required to achieve the fire endurance, that sacrificial layer. Since CLT is a proprietary product, the designer will need to contact the manufacturer of the CLT to obtain the net section properties of the CLT and then determine the structural capacity of the CLT after it's been exposed for the desired period of time. A similar process of affecting the effective char depth provides a net cross section of effective residual cross section for CLT roofs or floors. To get a more in-depth example as to how this all works together, you can download our TR10, our technical report 10, and look over our example 4.6 for an exposed CLT wall. You can go to it's located on page 43 of TR10. It's important to note that you could also have both a calculated fire resistance of the exposed wood combined with added fire resistance of non-combustible protection on the surface of wood. It's a very significant and important point. This is what will distinguish wood from steel in regard to fire resistance methods. For wood, you can determine the fire resistance that is calculated according to the calculation method for exposed timber for the member. Then you can add the fire resistance afforded by the added non-combustible protection to come up with the total fire resistance of the element. So you can remember that you can accomplish the total required fire resistance with one, by sizing the member so that all the fire resistance can be accomplished through the calculation method of fire resistance of exposed timber, a method we will discuss more in detail in a moment. Or by sizing that, you can accomplish the total fire resistance by adding the total fire resistance to the outside of the wood member on the form of layers of gypsum or some other non-combustible covering. Or you can do both. You can take the calculation or the required fire resistance of the wood member itself, and then add the fire resistance of the protective layer. What that leads to is, for this graphic, basically, if you look at this building, consider that perhaps the CLT walls and floors shown in the project have been designed to have a specific fire resistance of, say, 1 hour. In order to achieve 2 hours, they decide to use a couple layers, 2 layers of 5/8 inch type X gypsum board on the walls and ceiling to provide the additional hour of fire resistance. The 2 layers of gypsum board provide approximately 80 minutes through generally accepted principles for fire resistance. Those are likely to become a part of the code for some of the tall wood provisions that you'll learn about a little bit later in the presentation. What I'm showing here, this is just a graphic showing the fire resistance rating achieved by adding the fire resistance rating of gypsum board, wall board, to the fire resistance rating of properly sized exposed wood members. So, as a summary, the fire resistance of traditional heavy timber is recognized solely by its minimum prescriptive dimensions. The fire resistance rating of mass timber is based on the calculated fire resistance of exposed wood. The fire resistance rating is based on its non-combustible covering, like gypsum wallboard, or it can be a combination of those first 1 and 2. And that gets us to our next poll question. Here's Marcy.
Excellent. All right. So our poll question is, calculated mass timber fire resistance can include which of the following? Calculated fire resistance of the wood, added fire resistance of non-combustible protection, minimum prescriptive dimensions, answers A and B, answers A, B, and C. So let's see, we've got about 30 seconds, so I'll give it about 5 more, and then we're going to close it. All right. And then, so 62% say answers A, B, and C, 37% say answers A and B, and that's about it, just a smattering elsewhere. So, Jim, I'm going to give it back to you to give us the right answer.
Thanks, Marcy. As you can see, the right answer is D, both A and B. You can get that with the fire resistance of the wood, and then added the fire resistance rating of non-combustible construction. Next, we'll go on and move to the IBC Tall Wood Building Ad Hoc Committee proposals. Basically give you a summary of those, that effort. The ICC board established the ICC Ad Hoc Committee on Tall Wood Buildings in December of 2015. The committee is made up of 17 members representing a diverse group of experts and stakeholders. This broad representation also comes from across the United States and Canada. There are 2 representatives from the states of Washington, California, and Illinois. 1 representative from the states of Ohio, Pennsylvania, Maryland, Massachusetts, Connecticut, Virginia, Georgia, and North Carolina, and 1 representative from Quebec. The representative, when you take a look at this, this slide, it gives you an idea on everything involved with the effort, the number of work groups that were appointed, how many major issues were identified, and then ultimately assigned to the work groups that were listed above. There's hundreds of reports and a whole bunch of information provided for you. You can locate all of that at the ICC Tallwood Building ad hoc proposals, the performance objective discussed and listed, and also that we developed proposals for the 2021 editions of the building codes. I wanted to note that the representatives from steel chaired the definitions work group, representative from concrete and masonry, was vice chair of the fire work group, and our only representative on the committee, he was basically, I think he referred to himself a couple of times as the worker bee. He was the one on the committee that pulled together, tried to keep track of all of the information that the committee was asking for, and then helping to pull together that information so that the committee could proceed and work efficiently. This basically, the Tallwood building, we had, these are the ad hoc objectives, and what they wanted in the end, they wanted to make sure that there was no collapse under reasonable scenarios of a complete burnout of fuel without sprinkler protection being considered, no unusually high radiation exposure from the subject building to adjoining properties, no unusual response from typical radiation exposure from adjacent properties to the taller wood buildings. And there, last but not least, the last set, no unusual fire department access issues, making sure that the fire department is not adversely affected due to the mass. Egress systems designed to protect public occupants during design time escape, plus a factor of safety. And then highly reliable fire protection suppression systems to reduce the risk of failure during reasonably expected fire scenarios. I put this here. This basically just provides you with a link that you could go to that provides you with a complete monograph for all of the Group A proposals heard in Columbus in April. Included is G108, the one that we have referenced here, which deals with the type of construction subjects. One of the main points that makes up the code change proposals for the Tallwood Building ad hoc. We also provided you with the address for the link that would take you to the spot on our website, where we have several pieces of information about the tall mass timber effort. The list of 14 Tallwood building proposals, proposed review guide, so that you can have an effective methodology for going through and reviewing those 14 proposals, type of construction comparison, and a link to the full webinar on the changes. In addition to the current type 4 type of construction, one of the things that the proposal does is it provides, adds 3 new types of construction, types 4A, 4B, and 4C. The current type 4 is to remain unchanged, except for its designation, which will be changed to type 4HT. This slide, what I've got on the slide here in the red box is the new types of construction shown in table 601. So you'll notice the various fire resistance ratings. One of the things that's interesting to notice, if you take a look at the column for type 4A and then take a look over to the left at the column for type 1A, you'll notice that the fire resistive ratings are the same here as they are here for type 4A. The column headed, now the one thing, even though the column heading is HT, this column right here, this basically, I just bumped forward. That column basically stays unchanged from the current type of construction. So that's the current type 4. What I have shown here are some prescriptive ways to comply with the required non-combustible protection that's called for in tables 601, the previous table you looked at, and then 602, the bearing wall table that's pointed to from table 601. Just gives you the how it can be provided, what one layer, what the fire resistance rating of the element is for one, and then how much fire resistance you can get by using 1/2 inch of gypsum board or 5/8 inch thickness of gypsum board. Another a little bit different than the current type 4 heavy timber is that concealed spaces are going to be permitted, but no exposed combustible materials are permitted other than those normally approved for plenums, such as gypsum wallboard, plenum-rated cables, etc. This slide is really significant, and this was a provision, the non-combustible provision. AWC pressed for this limitation to disallow the use of combustible materials, foam plastic insulation, outboard of the mass timber exterior wall. We wanted to be reasonably assured that a fire like that of the Grenfell Tower in West London could not occur in one of these new types of construction. This limitation for that non-combustibility, except for the water-resistant barrier, is in place for each of the 3 new types of constructions. Here's a graphic representing the concept of the 15-foot separation that is called for when you're dealing with making sure that any of the exposed wood that's allowed for like type 4B is separated for that 15-foot separation, so that you don't have a wall, an unexposed section of wall immediately adjacent to an unexposed section of exposed ceiling. It is a limit on the amount of combustible surfaces that can radiate heat from one surface to another. What I've provided here are just some of the type 4C important points that are significant about it. The interior faces may, in this case, be all unprotected. Exterior sides must be protected 40 minutes. Floors must meet the provisions of 804, Section 804. Concealed spaces, again, although permitted, must be protected. No combustibles other than those allowed in a plenum. And the shafts must be protected inside and on the room side with non-combustible protection for 40 minutes. This next slide shows the modification between the early concept that was considered for proposal by the CLT and the Columbus proposal. It was modified a little bit, and this shows you how it was modified to make sure there is no delamination based on conformance with the heat performance requirements of DOC PS1. Once it was determined that the 2018 edition of PRG 320 included those heat performance criteria and would also be the edition referenced in the IBC, the appropriate section of PR 320 was instead pointed to. These are a couple more of the special provisions associated with the proposal. First refers to the need for the sealing at the intersections of mass timber elements. Second is the need for the special inspection of those the sealing of those intersections. It's important to note that the proposal under special inspections will be the special inspection part of it. That will be proposed as public comment to that to be considered in Richmond this fall. These are a couple more of the detailed provisions associated with the installation of the gypsum board non-combustible protection. Basically provides that prescriptive nailing or screwing patterns that are necessary to keep the layers of wallboard in place. You'll remember that I noted a little bit earlier that we're looking for enhanced suppression. This shows the added text calling for the enhanced water supply, that will be provided at the 120-foot height for buildings of type 4A and 4B construction. Now, the significance why it's enhanced is that that trigger that you have, that enhancement, is not triggered for other types of construction until the 420-foot height. What I have here, what I provided for you here, is a graphic representation of the fire safety being required during construction. One layer of non-combustible protection if required on all mass timber more than 4 stories below the uppermost floor under construction. The exterior wall coverings on all floor levels more than floor levels below under construction. And that includes the mezzanines. So it shows you how it steps up as the construction above proceeds. The covering of the exposed wood below also proceeds. Here's what we have. What we have for you here is kind of a overall summary of the graphic representation of the allowances and limitations associated with type 4C construction. We're going to have, I've got some slides, the next couple of slides show you what's provided for 4B and 4A. So as we move from slide to slide, you'll just want to take a look and compare the maximum height, number of stories, the exposure that's there for provided, the sprinklers are required, the basic fire resistance ratings for the primary frame and floor, and then information about the stair towers and the concealed spaces. Here's that graphic representation of type 4B. You'll notice that it's allowed to be considerably taller than 4C as far as height. The numbers of stories go up. Exposed gives you the basically the outline on the exposure and then the fire resistance ratings. This is the last of the graphics on the types of construction for type 4A. And again, it shows you this is the tallest of the types, recognizing the fact that all of the mass timber itself is going to be covered by substantial layers of drywall. And the numbers of stories, the ranges that were included in both type 4C, 4B, and now on this slide in 4A, the ranges are there is because the number of stories that are permitted, if you'll remember the type, when you're dealing with the table on heights and areas, it varies based upon the occupancy and use. So for instance, the 18-story that's listed here, that isn't permitted for all occupancies, but it is permitted for like residential and the business occupancies. And with that, now we're up to another poll question for Marcy. All yours.
Perfect. All right, so which of the following new types of construction are proposed for the 2021 IBC? Is that A, types 5A, 5B, 5C, or answer B, types 4A, 4B, 4C, or answer C, types 4A, 4B, 4C, 4HT, or answer D, types 1C, 2C, 3C. So we've got about 55% say types 4A, 4B, 4C, 38% letter C here. So I'm going to send it back to you, Jim.
Thanks, Marcy. And again, the answer is type 4A, 4B, and 4C. So the answer is B. Now, I noticed when Marcy went through the poll that I think it was 38% picked C. Now, I want to give a little credit to those of you that did choose C. The distinctive, the reason that the answer is type B is because the types of construction and all of the criteria as far as the fire resistant rating, that's what's new, is for type 4A, 4B, and 4C. It's only the title that changed for type 4HT. So if we're thinking, well, maybe this was a trick question. We don't try to do trick questions, but you were thinking that, oh, they changed the title from type 4 to type 4HT, and that then is included. So I'll give you a little bit of credit for that. Now what we'll do, we'll move on and we'll provide you some information about mass timber and the fire testing associated with that. The purpose of basically the fire research that was pulled together, we wanted to perform tests of realistic fire scenarios applicable to tall wood construction in order to evaluate occupant and firefighter tenability for egress and suppression efforts, and to provide data necessary to guide further development of relevant code and standard provisions by the Tall Wood Building Ad Hoc Committee. The tests were conducted at U.S. government facilities, basically the ATF test lab in Maryland, supervised by U.S. Forest Product Laboratory staff. This side, what we've done here shows the basic layout and the size and configuration of the two-story building chosen for the fire testing. You can see that it's going to be a two-story configuration. The interior dimensions were basically 30 feet by 30 feet. There was provisions for a corridor and a stairway that would wrap around the unit. The facility to be loaded with more along the lines of the modern furnishings fuel load. We were hoping to, or what we were struggling, or what we were choosing to shoot for, was the fuel load of 550 megajoules per meter squared. Fuel load approximated 95th percentile of Group R fire loads from a survey of Group R occupancies. This is just a picture looking down as they were basically finishing up the construction, just getting to the installation layers. It's a view from the control center at the ATF test lab. Here's a photo, the interior of the ATF test structure, showing the interior surfaces that are taped and mudded, or as they're in the process of being taped and mudded. Looking from the location of the kitchen out the door leading into the corridor. This picture was taken before they had completed the installation of all the gypsum wallboard protection on the mass timber surfaces, and before they had constructed the steel stud interior partition infills, one of which was basically over here in this area. What we have here now is pictures of the interior. Notice that the wood cribs that were added to the content to approximate the desired fuel load. This table, the table that you have before you now, gives you an indication of the 5 tests that were provided and a basic description, along with the date that they were conducted. First, for test number 1, all of the surfaces were protected with 2 layers of 5/8 inch type X gypsum wallboard. For test number 2, 30% of the CLT ceiling area in the living room and bedroom were exposed. In test number 3, 2 opposing CLT walls were exposed, 1 in the bedroom and 1 in the living room. You'll note that there is a partition wall, but that was the metal partition wall, and that's not exposed. In test number 4, all mass timber surfaces were fully exposed in the bedroom and living room. And of course, not the bathroom, which is constructed completely of metal studs and drywall. Again, in test number 4, there was sprinkler activation, normal activation. Test number 5, all of the mass timber surfaces were fully exposed in the bedroom and living room. Again, not the bathroom, as in test 4. It was provided with sprinklers, but the delay of the activation for the sprinklers was put into place, and that delay was a 20-minute delay. These are some pictures showing how they are loading up for the test. All the surfaces, you'll notice all the surfaces are covered, protected with 2 layers of 5/8 inch Type X gypsum wallboard. Again, this is test number 1. So here we are. This is just a few slides that shows the basically the progression of the test itself. Over on the left side, you can see the glow in the lower left unit. That's right after they started the ignition. The living room, basically the fire on this side then was in the flashover stage here in that picture. Next picture, we have the adjacent room or the bedroom area flashover. As it moved to the decay phase, and then a couple of pictures as it was basically self-extinguished. This is the picture over in the living room kitchen area and then the bedroom area. Again, in the end, self-extinguished. This is just a picture. This is a picture from up on that control room again. It shows towards the very end of that first fire test, and it shows just a little bit of content still glowing as we reach the, where we're getting near to the end of the test. Now on to test number 2. This is, again, to refresh, this is where we had 30% of the CLT ceilings exposed. And it was, the exposed areas were provided in both, one in the living room area and the other in the bedroom area. The live load to basically identify the load carrying capabilities were not affected was applied using water barrels. What I have for you here are just some of those pictures similar to that for test 1, showing the ignition and the fire right in the corner there. You can see that it was glowing. The next is the kitchen, the kitchen living room flashover, then the bedroom flashover. At that point in time, it was then moving into the decay phase. And at the end, it isn't showing the total of the end, but it's showing the exposed portions and the charring associated with the exposed portion in both the living room ceiling and then in the bedroom ceiling. What I have for you now is a short video of that second fire test. So we'll move through this. You'll notice it's at the speed will fluctuate basically to move things along. You'll notice at the very beginning you had the firefighters. They were entering the area to start the fire. The decision was made to start the fire in the kitchen cabinets. AWC, we had originally suggested that the fire should be started in, like on a couch, representative somebody smoking in the on an upholstered foam surface, but the decision was made instead to have the fire started in the kitchen cabinet, the lower kitchen cabinet there. Then speed moves forward in time. And you can see the various, you can see over in the lower right, the thermal cameras. You can see how the heat is better and temperatures are rising in the living room area on the left. And we're pushing over in the basically on the left-hand side. For those of you that like watching these fire tests, you'll get a kick out of how quick it goes up once it reaches flashover. And we're speeding up again so we get to the next, so we can get to the next flashover. Now, the one thing, what I want to do is I want to show you down here in this. This is the screen that's a shot of the 20-minute door assembly, and you'll want to take a look at that, and I'll comment a little bit. But as you can see, we're getting very, very close to flashover in the second part of the unit. It's kind of, it's somewhat of a point of interest, but we were very happy that the flashover, what you'll notice for the flashover here, was almost exactly to the second to the flashover that occurred in both tests 1 and 3 as well. So as you can see, there's the flashover. So it was right at that 17-minute and 20 mark. Why that was so important is, of course, we were loading all those extra wood cribs in there and trying to make sure that we replicated the same fire load in the same condition from tests 1, 2, 3, 4, and 5. Now, as you watch, over here, I talked a little bit earlier about that 20-minute fire door. We had there were thermocouples and monitors all throughout the assembly, or this model. And what's significant, the reason that the corridor is so significant and the provisions associated with the corridor is we wanted to make sure that there was tenability for the occupants to get out, and also tenability for the firefighters who would be accessing the in the fire condition. And you'll see that it was at that the doorway itself lasted quite long, and it was almost a full hour before it fell out. And by that time, the fire on the inside was starting to degrade. So the tenability of corridor remained quite low, or quite usable. Now with this next, what I've done in the next slide, we made a comment about the difference in the test number 3 and the exposed wall, and what I've tried to do here is just point out where the those exposed walls were. So you got wall D and then wall B. Those are CLT walls, and those were fully exposed in this test. Again, as with the other tests, the fire decayed with no reignition, so basically it's self-extinguished. Test number 4, what I've got before you, test number 4, again, all mass timber surfaces fully exposed in the billet bedroom and living room, sprinkler under normal activation, and as you can see, when the activation occurred right around 3 minutes, and it suppressed the fire. Fire was contained, and as you can see, it was contained essentially to the cabinet of where it was the fire source started. This slide shows you the test number 5, which had the delayed sprinklers. Again, fully exposed, all mass timber surfaces fully exposed. Sprinkler activation was delayed for 20 minutes after the smoke detector activation, which essentially is about the same as the fusing of a sprinkler. So at approximately 23.5 minutes from ignition, the detector was, or the sprinklers were charged, and the fire was suppressed. We were not sure. We were not sure what would happen with the delayed sprinkler activation. In essence, what happened was the piping got so hot that when the water was turned on, it immediately turned to steam, and the steam displaced all the air in the room, quickly putting out the fire that was nearly at flashover at that 23.5 minute point. So to summarize, basically, mass timber as a separate building system was really born because of one product, cross-laminated timber. Never before have we contemplated solid wood floor and wall sections being used in a similar manner as concrete, walls and floors. CLT is typically dimensional lumber, 2x lumber, laminated in crosswise fashion, layer upon layer. There's an odd number of plies, 3, 5, 7, 9, to make a solid wood wall, floor, or roof panel up to 20 inches thick and 60 feet long. Typically, what you'll see there is a 7-ply panel that's about 9 5/8 inches thick. A 3-ply panel is about 4 1/8 inches thick, and a 5-ply panel is about 6 7/8 inches thick. Here's that view of the model structure being corrected, just to basically give you one last look at the size of these mass timber CLT products. Here we are with Marcy for the final poll question. Marcy, it's all yours.
Okie dokie. Which of the following statements about the ICC Tall Wood Building Ad Hoc Committee fire tests is correct? A, 5 fire tests were performed. B, fire in the CLT test number 2 eventually self-extinguished. C, CLT remained structurally sound after fire exposure. D, sprinklers put out fire on exposed wood. Or E, all of the above. All right, so 88% say all of the above, and a smattering for the other answers. Jim, take it away.
Thanks, Marcy. And the answer is all of the above. Good. Everybody got that one. Thank you. And with that, we're at the end of the seminar, and I want to thank you for joining us. And, Marcy will close us out with a little bit more information before we get to the Q&As.
Actually, Jim, since we've got some time left before the top of the hour, I think we're going to go ahead and do the Q&A now before we close out. So sorry to throw you a curveball there, but we got some good questions.
Okay.
One of those had to do with penetrations, the fire tests that were done at the ATF lab. Talk a little bit about penetrations and how those were either tested or how they would be dealt with in CLT or mass timber construction.
Yeah, thanks, buddy. The actually all of the penetrations, when the model, or when basically the 2-story structure was constructed, the plumbing was installed and associated with all of the fixtures. So, and then also for the sprinkler piping. So there were through penetrations, which in the case of the test, what we did is we made sure that those penetrations, because these were fire resistive rated assemblies, that those penetrations were properly protected as would be required by the code. We used different types of materials. So we had the penetrations for piping. We had penetrations for electrical. We had the penetrations of the thermocouples themselves. But in all of those cases, we used the appropriate fire protection through penetration fire stop methods to provide the protection, and they were all monitored. They all were successful. In the tall wood building ad hoc proposals, there are no proposals to change through penetration provisions. So the through penetrations, how they're dealt with, whether or not it's a through penetration system associated with the pipes, electrical units, basically your utilities, or whether it's a duct penetration, or whether it's a gap, the joint, the gap associated with a need for movement, which would have to be protected as required for joint protection in the code. So
Great.
There's nothing different.
Yeah, similar question had to do with connections. How were the connections protected?
Well, the connections, what they did is they used an adhesive or in the case I think this I'd have to check into to be sure, but I think they may have used different types of sealants. But that was one of the requirements that that were put into place by the Tallwood Building Ad Hoc Committee. They knew that there was potentially going to be just some spaces for not gaps for movement or anything, but just the gaps or the little cracks and crevices associated with normal construction, and they wanted to make sure that those were not going to have an effect. So the actual code change proposals are demanding or calling for the sealant, and that was after after seeing how well that sealing of the intersections worked in the test assemblies or in the fire tests.
Yep. The other thing to add, there's NDS National Design Specification Chapter 16 requires protection of connections with wood or gypsum or some other method like those sealants that you mentioned to last or to get through that fire, whatever fire endurance is required. So good. That addresses that question. Another one that came in here that you can address. Sometimes we mention mass timber. Sometimes we say heavy timber. What's the difference?
Well, basically the difference between mass timber and heavy timber is we're trying to differentiate the use of the term heavy timber as a type of construction and mass timber as the whole of the current type 4 heavy timber, or which in the new proposals is type 4 HD, and then the newly added 3 types of construction for type 3 or type 4A, B, and C. The main difference is that for the historic type 4 heavy timber, there are no fire resistive ratings specified. They're assumed to be provided by the mass or the size of the heavy timber, but for all of the mass timber that we have with the new types of construction, if we can go back and we can take a look back at the slide if I can get there quick enough, but we actually have in the table, we have all of the fire resistive ratings called out for the type of construction. And I'm not going to be able to get there quick enough.
Well, that's okay. As I recall, one of the committee members said that the ad hoc operated with a do no harm to heavy timber sort of perspective, where heavy timber provisions did not change. But when we added the new types of construction, mass timber, those are all calculated, correct?
They have to be, yes, calculated or tested, but you have to provide where it's calling for. Here's actually the table. You'll notice over in the HT column, that's where the do no harm took place. And you'll notice that there's no rating called for other than in the exterior wall, very few. Over here, every cell is filled with a fire resistive rating requirement, other than, of course, interior partitions, which are the 0. And in those cases where, like for instance, where you have the 2-hour rating or the 3-hour rating, you're going to have fire resistance established by, typically, because of the mass, that calculation methodology of the mass timber with the additional protection of the drywall, like shown up here in this table. Great.
And then there are a whole bunch of requirements for this protection, this non-com protection, for how it's attached to the mass timber to provide that additional time. So if you could jump back up to that slide you were on a second ago, there were a couple other questions with different types of construction. Is it true that types 1 and 2 allow for heavy timber or mass timber to be used in type 1 and 2 construction in certain instances?
Very limited instances. I think there's a footnote relative to the table, and I can't remember what the specific criteria are, but it's typically up in the roof as far as certain, you can substitute out heavy timber in certain applications.
Yep, good. Then for something like type 5 construction, can you mix, say, heavy timber, prescriptive heavy timber elements into type 5A, for example, if you had a requirement for 1 hour in type 5A, would you still have to calculate, say, a glulam beam if it met the minimum heavy timber dimensions?
I'll say what I always say. There are a considerable number of code officials who will routinely allow the use of the heavy timber of the correct minimum sizes as a 1 hour substitution, but the code doesn't allow that. So in reality, what you really need to do, where it's calling out for 1 hour, you would need to actually go through that calculation, using our Chapter 16 to establish that that 1 hour fire resistive rating for the glulam. Again, one thing that I don't think we touched on in here is when you're dealing with the glulam, the fact that you have to add that one extra layer out in those tension, the tension laminations.
Good, very good. Well, Jim, we're a little bit past the top of the hour here, and thank you for a great presentation today.